Good morning. So my name is Massimo Scandura. Some of you maybe are new to the observatory. So just a brief introduction to explain the main targets and the main organization of the network. So we are an open network. Anybody who can contribute with the observatory observation site, so can contribute with the study area in Europe, can join the observatory. And we have some steps that are composing the participation to the network. The first is the agreement that is signed by the coordinator of the INET12 project and the participant who is going to join the network. The second step is to participate in the training, the first training, that is the training of today, dealing with the study design and field work. The third step is data collection that usually starts at every annual campaign in July, more or less, in June, July, and can last, depending on the duration of the deployments, until the late autumn or early winter. And then we'll have a second training after summer in September, when we are approaching data analysis, and the second training is focused on this part, on the management of photos and the data analysis part in Agouti. Then after this training, at the end of data collection, start the data analysis that is going to use the platform Agouti and the R scripts proposed by the observatory. And at last, we have the submission of the results that are shared, checked by the EOW staff, and they will be shared with the community in an open database. What we offer collaborators a series of supports and tools, so the protocol, the training like today, continuous support, online support by email and during the meeting and so on. We offer the implementation of Agouti as a platform for data analysis and data storage, and then dissemination of the results on the European Food Safety Authority publication, and also participation, contribution to conferences, congresses, and we have started the collaborative approach to publish scientific articles. Collaborators are requested to adhere formally to the network through the agreement, indicate a reference person, provide information on the study sites, and apply the protocol. We recommend to strictly apply the protocol and provide results, share results of the analysis at the end of the analysis on time, possibly on time, in the form expected by the observatory. As we all are part of a network, it's important that everyone is joining the network, participate in a correct way, and complies with the protocol, with the EOW recommendations, and submit and share the results on time. So these two aspects, protocol compliance and punctuality, are important to have the data fully comparable at the end, and they can be all collected and shared in a public database and be ready to be used also for data analysis, for scientific publication. So this is a very important aspect to stress today. Then in the last year, we have updated the website, so you can find the site of the website or the website of the observatory, a simplified version of the previous website with updated information, including the information on participants and study sites that appear now on the map of the website. Two other very important implementation and the improvements were done in the last year. One concerns the publication of the policy that concern data access and data use of participants of the observatory, and also the workflow to propose papers and participate in collaborative publishing. The second important implementation is the renewal, the re-editing of the database containing all the data collected in the previous campaigns by the observatory, that is already available in Zenodo, but is going to be updated with the results of the last year, 2024, and it fits the requirements for data and metadata sharing in open science. That is one of the main recommendations of the European Food Safety Authority, the committer of the project. So these are the introductory information I wanted to give you concerning the data used for publications. We will have at the end of the training, for those of you who can stay, we will have a proposal by Joaquin Vicente that will introduce a pager for a publication, a new publication. And I want also to apologize because at one moment I should leave the call to take a flight. So I greet you now and leave the floor to Tancredi for starting the training.
Great, thanks, Massimo. So I would say that we can now start with the actual training. So I'll share my screen. Can you see it in presentation mode?
Yeah.
Perfect. Yes.
Okay, great, thanks. Yeah, so as I said earlier, my name is Tancredi Guerrazio, and we'll start now with field protocol. I will just take the chance for a couple of quick reminders first. So as to conclude the 2024 data collection campaign, we still need to receive a few results. So please, whoever didn't do that yet, take all the efforts to manage to finalize the analysis and provide the results. And also, as you know, we've asked to rerun the analysis from previous years, because the new format that we've been introducing this year requires the old results to be analyzed again. It really is straightforward and not very time demanding, because no further action is required on Agouti or anywhere else. It's just a matter of running the analysis themselves, running the new code for the creation of the CSV file, and submitting the results via the results form. We will send all the links, the necessary links, once again in the minutes of this meeting, but I just wanted to take the chance to remind this. Also, the start of the 2025 campaign, it is crucial that everyone who's interested in joining the campaign to submit the 2025 participation form. This link is also going to be shared once again, but that is fundamental for us to have a good idea of who is participating, what are the study sites that are proposed, and also to get the agreement signed, and so that we can actually start. In fact, the agreement is included together with the study site info file within the form. You can download them, sign them, and fill it in for the study file info file, and then submit it together with the form. So this is the roadmap. Massimo already mentioned it, but here you can see also some dates. So the agreement should be signed as soon as possible so that we can deal with the resources allocation and ship the equipment. Also, you will find in the participation form a box where you are asked to specify if you have any requirements in terms of funding or equipment, and to explain why you need it, so that we can assign the resources that we have, which are limited, in the best possible way, and make sure that everyone can participate at their best. So in early summer, we're gonna start the actual field activities, and we will, as EOW team, start analyzing and modeling the results from 2024 in summer, and producing the report, which is due to September. In September, we're gonna hold a second training course on analysis and Agouti, and for early 2026, we expect to receive the results. So now, with the actual training, there's going to be a very few very common principles, but this is going to be just a very quick introduction. So what we aim at is density, which is a number of individuals per area. As you all know, there's a very wide range of different methodologies that have been developed for this purpose. Each one has pros and cons depending on different factors. So we have many different ways to obtain densities, from genetics to area counts. There's no right or wrong methodology. All comes to what are the species, the habitat, the budget. So there's many different variables that can make methodology correct or wrong for a certain monitoring. So in our case, we are using camera traps. So our methodology is camera trapping. Why this choice? Well, the main reasons are, one of it is certainly a limited cost, which is limited to an initial investment, which is, however, then diluted in time, because then cameras can be used for several years and many different projects. A limited effort, because you can have the cameras running for a very long time with only requiring an initial effort to set them up and then to pick them up, while for the image processing, which certainly is an effort, the AI development is and platform development for the management of camera trapping projects are providing more and more help in this, reducing the workload consistently. Then a very important feature of camera traps is the fact that they allow the simultaneous monitoring of different species, which is not the case with most of other methodologies. And as it is for our protocol, we are trying to monitor many different species with the same activity. And this, we believe, is a very important feature. And finally, they are relatively easy to use, so anyone can learn fairly quickly how to use them correctly. When it comes to camera trap related methodologies for the estimation of wild population densities, we have two main kind of monitoring. So there's one with an individual identification of the animals, and the other one without individual identification. So for the first case, so where animals are individually recognized, we have sort of capture recapture kind of methodology. There's a few constraints, because the first one is the fact that very few species are actually individually recognizable at their natural status. So that is usually the case of felids, which are recognizable due to their unique fur pattern. But otherwise, it is very hard for us to distinguish from one individual to another. The other option is a marking activity, which, however, requires a very great effort, and therefore one of the pros of camera trapping is going to fall, because marking activity is going to require a lot of money, a lot of people, a lot of effort. So this could be complicated and make things more difficult. On the other hand, if we are implementing a methodology that do not require individual recognition of individuals, identifications, this is going to apply to most mammal species, and especially species which are usually relevant for management purposes, such as canids, ungulates, such as wild boar, and such as cervids. As for the methodologies that provide density estimates without individual identification by means of camera traps, the three main, there's many, but the three most recognized methodologies are the random encounter model, the random encounter and staying time, and camera trap distance sampling. They do share similar assumptions, and they have a compatible experimental design, and they all require to identify the position of the animal in the field of view. So in our case, the choice was to use random encounter model, which was proposed by Marcus Rocliffe, who is also participating in the observatory and in this training with others. And this choice was made due to the fact that this methodology has been widely used in the last years, and has proved to be effective and reliable, as it was also proved by many papers. And in this case, for example, the one from Pablo Palencia, who's going to speak after this presentation, where a very large number of papers where random encounter model was used were analyzed, proving the effectiveness, let's say, of this methodology. So a very quick look about the random encounter model formula. So here we have a y divided by t, where y is number of encounters and t is the time of activity of the monitoring, and this element is the encounter rate, so the number of animals detected per sampling unit. The higher this is going to be, the higher the density estimate is going to be, of course. Then we have V, which stands for day range, which is the distance that is traveled by, in average, by a certain species, an individual of a certain species within 24 hours. As you can see from the position in the formula of this element, the higher this value is going to be, the lower the density estimate is going to be. And then finally, we have R and theta, which are the effective radius and angle of detection of the camera trap. So the surface, let's say that the detection zone of the average detection zone of our camera traps. A very important part of random encounter model is the study design. In fact, as the name suggests, the camera placement must be random with respect to the animal movements. And this is crucial for successful implementation of this methodology. So how to produce a random sampling design? Well, here, just to simplify, I brought two examples, which we can usually adopt as main example of random design. One is a fully random design where each point is independently placed with respect to the others. So it is, as you can see from the image, there's no relationship in terms of distance from one point and the others. And the other one, as I said, there's few others way to create random sampling designs, but this is just to simplify. The other one, which is the one that we adopted, is the systematic random design, where basically each camera location is in a regular grid and with an equal distance from the next camera location. This design can be produced very easily with any GIS software, but alternatively, a specific app has been created to produce a regular grid of points. Basically, you will find also this link and instructions in the protocol file that we will share once again. And there you'll be able to upload a KML file that you can easily create on Google Earth and specify how many camera trap locations you want to create. And the app is going to create them for you and then give you the possibility to download them and then open the file in any GIS software so that you can directly then go to the field and look for the correct spot. So how many deployments should we do? How many camera locations? So a higher number usually provides a better precision of the estimate. So in general, we would say the more the better. Clearly, not everyone has an endless number of camera trap available. So 36 camera locations has been found to be the minimum number to obtain reliable estimates. And we'll explain here with this graph, which was taken from Paolo's paper, that the one that I mentioned before. I'll quickly explain why we will tend to have a higher number whenever possible. So basically, this graph is showing the relationship between the number of camera trap placement, so the number of camera trap locations that we have on our study site, and the coefficient of variation, and therefore the precision of our estimates, where a higher coefficient of variation corresponds to a lower precision. So what we're looking at here, the two lines describe how the precision of the estimate change with respect to the number of camera trap placements in two different populations. So K describes the distribution of this population, so whether the population is aggregated, the aggregation of this population. So a lower value of K describes a more grouped population. So the pale line describes a grouped population, while the dark one describes a population which is more uniformly distributed over the territory. So as you can see here, for a population that is not very grouped, a low number of camera trap placement is going to ensure satisfying precision rates. In fact, you see that with 20 camera trap placements, you already have a coefficient of variation which is lower than 0.2, which is usually the target when we are dealing with wildlife management. However, we can't say the same thing for the grouped population. In fact, you can see that in that case, where the population has very high, is very grouped, you can see that in order to obtain a satisfying precision rate, we have to go all the way to 60 camera trap placement. So whenever possible, the ideal number of camera trap locations or placements would be 60. This cannot always be the case, but whenever possible, we should aim for that target. So it might be 50, it might be 40, with a minimum of 36. Clearly, not everyone can always rely on 60 or 50 camera traps to be used all at the same time. So in these cases, it is possible to perform more sessions. So as you can see here in this study site, which is a study site that we monitor here in Tuscany, we've been implementing two different sessions. So we had 20 camera traps available, which were first deployed in the green session that you see here, and then they were removed and placed on the red dots for the second session. So depending on how many camera traps are available, we will always aim for the least number of sessions which are necessary to monitor all the points. So whenever possible, we will go for a single session. That would be the best option. But if it is necessary, we can split, let's say, or divide the overall number of camera trap locations in a subset, and then monitor them in one session after another. What is important, as you can see here, is that each session monitors the whole study site. So you can't split the camera trap location in north and south, but as you can see here, the green and the red sessions are spread all over the study site, and this is important. Also, the duration of the monitoring of activity of each camera trap should be at least 4 weeks, if possible 6. This also can be can depend on whether you are performing a single session. In this case, it might be easier to have a longer monitoring period, so you can easily go to 6 weeks. While if you have 2 or 3 sessions, then it might be trickier to get longer period for each camera location. The period of implementation that is suggested by the EOW goes from early summer to autumn generally, but this can also be discussed case by case, depending on the constraints of every study site and the needs of every collaborator. But we are trying to have harmonized monitoring, and therefore also to harmonize the period of implementation. So what camera type should we use? Well, basically, as for the technical specifications, any recent camera trap can be used. However, there's a very important aspect to consider, which is the fact that now are being more and more used recently camera trap with dual lenses, which have one lens for daytime pictures and another one for nighttime pictures. Those camera traps are not compatible with the protocol. I mean, they can be used, but they would have very big constraints, and you will have better understanding of this after the second presentation that Pablo is going to make about photogrammetry, which basically Pablo is going to explain why we do need calibrations to be done in the field. And dual lens cameras would require double calibration, and still there would be then issues in the digitizing of this calibration. And therefore, it is crucial that if you are choosing the cameras to use in this monitoring, that you make sure that your camera is a single lens. There are clearly, you will find this in the specs of the camera model, but you can easily see as the single lens camera have one lens. And so this is very important, single lens cameras for this, for our protocol. So in the field, a crucial point, as mentioned before, is the random placement, the placement of the camera on the random generated point. So for this to be respected, it is crucial that you get as close as possible. Possibly you get actually on the point when in the field, and if not possible to get actually on the point, then you get as close as possible to it. If the selected point is not suitable for the camera placement, then you should find the closest suitable spot, and if possible with the same microhabitat of the original one. When speaking about suitable point, we do not refer to a point that is suitable for animals. So we're not targeting animal presence. We want to monitor the random generated point. So when we're speaking about suitable point, we are referring to the camera placement. So clearly there has to be a tree where to strap the camera, or if you are in an open field, you might want, you're going to have to bring a post with you to strap the camera to it. But yeah, the spot has to be suitable for the camera placement, not for the animals. So you should resist the temptation to aim for good spots, because this is what we are generally used to do when setting up camera traps. We are targeting animal presence, but this is not the case. So this is very important that for us to stick to this principle. If possible, for a correct implementation of photogrammetry, if the ground in front of the camera trap is not particularly uneven, this would be better. And you will understand later on better when Pablo is going to explain this second part. If you don't find a suitable spot within 100 meters from the original random generated point, then you're going to skip that point, because otherwise you get too further away from the original generated point, and we don't want that to happen. The vegetation removal, this is something that we want to do in order to reduce the number of blank pictures. However, we don't want to drastically change the environment in front of the camera, as this would affect the animal behaviors. So we will reduce the vegetation removal to the first 5 meters in front of the camera trap, just to avoid that vegetation moving is going to fill in our memory card with blank pictures. So for example, here you have an example of a view from a camera trap. So you see that clearly the ground is not flat, but not particularly uneven, and the main vegetation just in front of the camera was removed. Whenever possible, the camera should be facing north, as this would avoid direct sunlight to come at the objective of the camera, blinding our pictures, and in some cases also triggering the camera. And finally, the camera should be set at approximately 50 centimeters from the ground, and the line of sight of the camera should be roughly parallel to the ground. So here's as an example. You can't really see the line of sight of the camera, but this is roughly how it should be. So that's approximately 50 centimeters. And from this angle, as I said, you can see the angle of the line of sight, but is following the slope of the ground, so being parallel to it. So what not to do? As I said, I'm going to repeat it once again. Do not place cameras inside that might be preferred or avoided by the animals, unless the original point falls in such place. So if the original point falls on a trail or near to a stream or a pond, then you can go for it. But otherwise, you should stick as more as possible to the original spot. For the same reason, we don't want to use baits or attractants whatsoever, and we don't want to reduce too much vegetation. So no engine trimmers or chainsaws are going to be needed in the field, but just hand tools are going to do the job, and so no need for any invasive clearing. And finally, you should, I'm pretty sure that everyone who used a camera trap already takes these precautions, but you should avoid smells on site. So smoking, eating, peeing should be avoided in proximity of the camera trap location. So what are the settings that we want to use? So camera traps should be active 24 hours per day, constantly, and we should we're gonna use picture mode with the highest possible number of shots for each activation. This usually is 8, but depending on the brand and model, this could be most of the time. In some cases, could be less. Anyway, we should aim for the highest possible. And we should set the burst mode, which in some cases is called rapid fire. This mode basically reduces to the minimum the time passing between pictures within the same activation. So we're gonna have for each activation, we're gonna have, let's say, 8 pictures in a rapid sequence. So we work with very short time passing between one shot and another. This is going to give us a high detail of the animal movements in front of the camera. The waiting time between activation, it has to be set to the minimum. This usually is 1 second, but anyway, whatever the minimum is. So basically we have a camera trap constantly working until there's something moving in front of it. Then, of course, we want time and date stamped on the image. Sensitivity can be set to low, and this is a compromise that we can adopt, let's say, in order to reduce the risk of our camera trap to be filled in, often by blank pictures in case of windy days and habitats with a high vegetation. And since our target species are medium to large sized mammal, a low sensitivity is still not going to affect our chances to detect these animals. The flash intensity can be regulated depending on your camera placement and depending on the settings that you have. If you can decide how you want to set your flash intensity, then, for example, in places with dense vegetation in front of the camera, you might want to set the intensity to low, as this is going to avoid overexposed pictures. While if in front of the camera you have an open area, you might want to set it to high in order to be sure that you are going to see further in the distance at nighttime. The picture quality should be set to the minimum, which is usually 4 megapixels, but whatever the minimum is, as we don't need nice pictures, we only need to recognize the animal and recognize their position in the picture. But for this, the minimum quality is going to be enough, and this is going to save a lot of space in our memory cards. And if possible, a very useful thing would be to set the camera to take daily controlled pictures. This is usually called time-lapse mode. This basically allows you to take pictures at known times during the day, in addition to the motion activated mode. So if you have this setting, it is usually provided in combination with the motion activated mode. But if not, make sure that you are using the combination of the two and not just the time lapse mode, because we of course need the motion activated mode, and if possible we want to also use the time lapse mode, because this is going to give us information of the camera trap activity. So if we have, let's say, 3-4 days with no pictures, we would have the doubt that the camera might have stopped working for those days, while if this mode was on, we're gonna have pictures taken even if nothing passed in front of the camera, having the proof that the camera kept working correctly. So this was it for this first part. Now we're gonna have, if there's any question about this part, we have some time for that. If not, there's gonna be also some question time at the end, but if some specific question about this part is asked now, I can answer it. Otherwise, we're gonna have a quick break before proceeding with Paolo's presentation. Yes, Delia?
Yes, hi there. Silly question maybe, but how do you decide the orientation of the camera in the exact spot you're supposed to put it?
Yes, as I said, the orientation should be north, unless there's some practical constraint in the field that do not allow you to do that. But you should always aim for north orientation.
Okay, thanks.
You're welcome. Yes, Astrid?
Yeah, same small question. what can be, if you have this controlled random grid, what can be the furthest or the closest distance between the camera traps? Is there like kind of an average?
So there's no an actual limitation for that. So cameras can be, there's no fixed measure or minimum or maximum measure. The important, if the design is respected, then the methodology is going to be implemented correctly. So what is important, as I said, is that the minimum number of camera trap locations is not too low. Otherwise, we're not gonna have solid result, let's say. While a higher number of camera trap location is going to reduce the variability and give satisfying results. But as I said, there's no minimum or maximum distance between camera placement.
Okay, so there's no effect if I would have like a grid of 250 meters or 1 kilometer.
Yeah.
Okay,
exactly.
thanks.
You're welcome.
So hello, my name is Pablo, and I'm going to explain you the implementation of photogrammetry in the context of European Observatory field campaign. So as Tancredi already mentioned before the break, just to estimate population density using camera trap and working with unmarked species, that's it, those species in which we cannot individually identify one individual or to distinguish one individual from the other. So we essentially need to estimate the location of the individuals in the field of view of the cameras, and this is common of all or most of the unmarked methods, let's say random encounter model or distance sampling or whatever. In all of them, we need to estimate the location of the animals in the field of view. So years ago, when we started with the NetWild project, we used to play a natural reference in the field of view of the camera. So here stones, but we also play branches and in general sticks. You can see here at known distance, for instance, 2.5 meters, 5 meters, 7.5, and so on. And then with this reference, here we have an example of a whale board recorded in a sampling point. So we then try to estimate the location of, as we can see here, of this particular whale board, which is close to the 5 meters reference in the center of the field of view. So we can say, or we estimate that the location of this whale board was here. So we used to work in that way years ago, but since the last 3 years, if I'm right, we started to implement photogrammetry in the context of the European Observatory of Wildlife and also in Agouti platform. So what is photogrammetry? Essentially, photogrammetry allows us to extract information about three-dimensional objects, in this case, wild animals, which were captured in 2 dimensions. So in a camera tapping picture, in this case. Here, we will use photogrammetry to estimate the location of the animals in the field of view, so the angle and the distance between the animals and the camera. But as you can see here, I just share a couple of examples in which photogrammetry is using in camera traps. So it can be used also, or is being used for estimate wild animal traits, for instance, antler size or body condition. And in this example, in this paper, they also use photogrammetry to quantify the severity of a skin disease. So it's also being used in epidemiology and pathology studies. So to apply photogrammetry, we essentially need 3 main steps. So the first one, or the first thing that we need is the calibration pole. I'm going to explain in the next slide how to do the calibration pole and how to work with it. We also need to calibrate the camera, the device, so let's say the Browning whatever, Browning Darkos Pro, whatever the camera you are using, or Reconis or whatever camera. And then the last step is to calibrate the deployment. That's it, the field location, the sampling point in which each camera is placed, okay? So starting by the calibration pole, essentially what we need, we can see here an example, is a pole with no reference. In this case, we usually work with reference every 20 centimeters. So we know that this reference is 20 centimeters in relation to the bottom of the stick, then 40, 60, 80, and 100 centimeters or 1 meter. So essentially we need an object of no distance and no size, which are placed in front of the camera, in the field of view. So how to do the calibration pole? So this is quite simple. I will show later a video, but what the materials that we need is essentially a pole. Around 1 meter is perfect, 1.5 meters, or even longer if you want, but around 1 meter, let's say. It could be plastic, metal, wood, whatever you want. This is up to you. And also in relation with the shape, it could be round or square, definitely up to you. We then need a Scotch tape, just to put this reference at no distance. It could be usually black and white is recommended, but if you, for instance, are working with a white pole, then obviously white mark don't make sense, so you can work with red marks or blue marks. Again, this is not relevant. The important point is to use a color which is clear different from the color of the pole, okay? Then we also need a measuring tape just to put the reference accurate in the pole, a marker and scissors.
Ако споро ради поново учи.
Here you have the video, which is online in the European Observatory website, also in YouTube, and I'm going to show you now. So in this video, we can show how to do the calibration pole. So here you have the materials, as I said before, the pole, in this case, a good pole, the scissors, the pencil, and the Scotch. So we first mark every 20 centimeters, as I said before, up to 1 meter in this case, okay? And the important point is that you mark exactly in 20, 40, 60, 80, and 100 centimeters, okay? And then it's very, very important that the upper limit of the tape is placed exactly on the 40 centimeters or 20 or 60, whatever, okay? So I will show you later again, but have a look here, and then if you cannot see properly in this presentation, then you have the video to check. But you can see that here the limit of these two marks, the upper limit is exactly at 40 centimeters, okay? In relation to the bottom of the pole. Yeah, always 1 mark. We put more than 1 mark just to indicate that allow us to know that, for instance, if we see here 3 marks and 4 marks, we know that these 3 marks correspond to 60 centimeters and these 4 marks correspond to 80 centimeters, okay? But the important mark is always the upper one. So you can see here that 1 mark will always correspond to 20 centimeters, 2 marks will correspond to 40 centimeters, and you can see here how the upper limit of these 2 marks are aligned with 40 centimeters. The same here, 60 centimeters, so 1, 2, and 3 marks, 60 centimeters on the limit of the upper mark. The same with 80 centimeters, and the same with 1 meter, okay? You can see here 1 meter exactly on the limit of the upper mark. So, and then we will go to the field. I can show you, I'm going to explain now, but then we'll go, oh, sorry. So, Here we go. So this is how to do the calibration pole, okay? Then regarding to calibrate the camera model, as Tancredi also mentioned before, you can use whatever camera you prefer, in case you already have some cameras. And to calibrate the model, most of the camera models, Ronin and many others, are already calibrated and available for free in Agouti. So I'm not going to explain how to calibrate the model, because I think that in most of the cases it's already calibrated. And if not, if some of you are using a camera which is not calibrated, we can particularly send a very simple instruction for you. But just the general idea is that most of the models, especially those provided by the observatory, are already calibrated and are already available in Agouti, okay? But the more important point for you, and yeah, for all of you, is to calibrate the deployment, because it's something that you have to do on the field, okay? And as I mentioned before, every deployment, so every sampling point, every location in which a camera trap was placed needs to be calibrated, okay? And as you can see here in this slide, it's very important that there are only one slope in front of the camera, so one slope in the field of view. So in addition of all the description that Tancredi said before about placing the camera on the field, regarding photogrammetry, the more important point is that only one slope should be in the field of view of the camera. So in this case, you can see here a bad example, which is an example with more than one slope. You can see one slope from this part to the other, as is indicated by this arrow, and another slope here. So this deployment is not appropriate, and this deployment will result in a biased photogrammetry implementation, which is not possible to use to estimate population density, okay? So this deployment with two or more slope, whatever these slope are in the field of view, it could be in this way, but it could be in many other ways. So this deployment is important and is not useful, and is not recommended to place cameras in front of this sloppy field of view, okay? So we need, or we have to place the camera with a field of view with only one slope. And as you can see here, this could be one deployment with one slope only, which is perfectly 0 degrees slope, let's say. But it could be also at maximum, like in this way. Here we have in a slopey terrain with high slope, but we only have one slope, which is essentially from upper right on the picture to bottom left, more or less. But even here we have a high slope. The deployment is appropriate, okay, because there are only one slope. And the same in the other direction. Here you can see another example with another slope, but we only have one from the upper left to the bottom right, let's say, more or less. So this could be also an appropriate deployment, okay? So I repeat again, it's important to place the camera just with one slope in front of the camera, or one slope in the field of view. So when we decide the location of this camera, considering the slope concept, but also all that the details that Tancredi mentioned before. So when we have found a tree or a specific placement to put the camera considering all the above, then we need to set up the camera filming. Okay, this is important to minimize the risk of the camera movement. So we set up the camera and we switch it on to record picture, as also Tancredi mentioned before. And more or less about 1 meter in front of the camera, just we start to hold the pole. Or it's important that the pole should be based on the ground, because you know that we place this 20 centimeters mark, so we need to put always the pole on the ground, and then we know perfectly the height of the pole, okay? And it's also very important that the pole should be perpendicular to the camera line or side, okay? So if the ground is the slope is 0 or almost 0, it will be simple. But if we are working in a slopey terrain, as we can show in this plot here, then the pole should be placed perpendicular again to the camera line of sight. Okay, this is also quite important. And then it's important also to hold the pole quite long, because you know that cameras are usually slow, are usually not as faster as we expect. So we can wait a couple of seconds, 5 seconds more or less, holding the pole perpendicular to the camera line of sight and resting on the ground. We can indicate with in some way, for instance here, thumbs up, that the pole is resting on the ground and perpendicular to the camera. And then we should avoid this example. For instance, here you can see in the bottom picture that the pole is not resting on the ground. So this picture is not useful to calibrate the field of view, or is not useful to apply photogrammetry. And in this case, you can see an example that the pole is not perpendicular to the camera. So again, this picture will not be useful to calibrate the deployment. Okay. And at the end, we need to repeat this process around 20-25 times. So we need to place the pole more or less around 20 different locations in front of the camera. And it's also important to place the pole covering all the field of view of the camera. So as you can see here on the left panel, there are some these crosses indicate the location of the pole. So some of them are very close to the camera, some of them far away, some of them on the right side of the camera, or they're on the left side. So essentially covering all the field of view. And yeah, here I indicate that placing the pole very close, so let's say that less than 1 meter away from one location to the other, more or less, this is approximately, is not very useful. I mean, it's not useful to place 20 times the pole, but essentially less than 1 meter, all of them, because we are essentially calibrating a very small part of the field of view. So the important point is to place the pole covering all the field of view and space it more or less around 1 meter or more than 1 meter apart. Okay. And then other important thing to consider is that the maximum distance here, the maximum radius to place the pole, will depend on its particular deployment. So if we are working, and I have now a couple of examples, but if we are working in an open grassland, for instance, if our camera is placed in an open area where the field of view is quite long, so we can place the pole until more or less 15 meters from the camera, more or less. Okay. However, if we are placing, if the camera is placed in a very dense vegetation habitat, and we can only see, let's say, more or less 7 or 6 meters from the camera, then don't make sense to put the calibration pole far away of these 6 or 7 meters, because essentially we will not be able to see the pole in the picture. So we need to calibrate the field of view in those parts or in those areas where we will be able to see the pole and where we will be able to see or to identify animals. Okay. If the field of view is open, then we can, yes, as I mentioned, work until 15 or calibrate until 15 meters more or less. If the field of view is very dense and full of vegetation, we can calibrate only maybe around 6 or 7 or 5 meters. Okay. And then I indicate here to repeat or to calibrate 20-25 different locations. This is because usually, despite on the field we calibrate 20 times, for instance, many of them, and I'm going to show you a couple of examples later, some of them will be not useful because, for instance, we are outside. We could think that we are on the limit of the field of view, but then when we check the picture on the computer or on Agouti, we will see that we were actually outside of the field of view. So then this location is not useful, and some of them, as I saw before, the pole is not resting on the ground or the pole is not perpendicular. So then from these 20-25 locations, some of them will be discarded. So at the end, we will work with around 15, something like that, useful and usable pole location. Okay. And yeah, here we have a couple of wrong examples. So for instance, here we calibrate only far away of the camera, and we have this zone or this part of the detection zone close to the camera is not calibrated. So this is not useful. Here we have the opposite. We only calibrate very close to the camera, but we have here a big part of the field of view without pole position, which is not calibrated. And then if we work only with 3 or 4 or 5 pole location, there are very few to fit an appropriate photogrammetry model. Okay. So I said before that we used to, or that we recommend to place the pole, or to start to place the pole more or less around 1 meter from the camera. This is just to allow us to at least visualize these two marks. In this case, 40 centimeters and 60, because there are 2 marks. So this is 40, and 3 marks here. This is 60. So this is important to place the camera at a distance that at least we can see 2 marks. Okay. If we only see 1 mark, then we cannot use this picture and this pole location to calibrate the field of view. And here you have a GIF provided by the Maria and Oscar, two collaborators of the European Observatory, and you can see how Oscar, in this case, is calibrating the field of view of one camera and covering from one side to the other and from far away to the camera to close to the camera, as you can see here. But it's important, as I mentioned before, see like here, for instance, Oscar went outside of the field of view. So this could be an example of one pole calibration or one pole placement, which cannot be useful essentially because the pole is outside of the field of view. Okay, so this is why I say that despite on the field we can do 20 or 25 placement of different placement of the pole, then some of them will be discarded. Okay, and here essentially the same. You can see another example, in this case picture of a really open placement, and you can see how the calibration pole is placed to the camera in this part. Then we have some of them on the left side, for instance this one. Another, the pole is also placed on the right side and on the central of the picture, here in the right side, the central of the picture, and so on, from very close to the camera to really far away, for instance this one, or also this one here. So this could be a good example of calibrating the deployment. Okay. And as I mentioned before, we have to calibrate the deployment when we place the camera. So at the beginning of the experiment, at the beginning of the field campaign. But if for some reason an animal or even us, when checking the memory or batteries, move the camera, we need to calibrate again the deployment. Okay. And also it is also recommended, to calibrate the deployment when we come back 1 month or 1 month and a half later to remove the camera. In this case, if during the sampling period, if during this 1 or 2 months where the camera was on the field, some animal, for instance, or something moved the camera, we have the field of view calibrated again to use this picture of this sampling period after the camera was moved. Okay. And now I'm going to share with you some habitual errors, so maybe it helps to avoid to repeat again. So for instance, remember always starting by the left side. So remember that one mark should be always placed close to the ground because it indicates 20 centimeters. Okay. So in this way, the pole is placed the other way around. So it should be placed in this way, as you can see here. Then the second example is that in this case, this collaborator is covering the upper mark, which are essentially the more interesting. So please hold the pole without cover the mark. Okay, so in this case, hold by this part, or you can also hold the pole in this part without marks, but never, please, never cover the upper marks. Okay. In this case, for instance, you have in this picture, we have an example of the pole place it very close to the camera, so we can only see one mark. So in this case, this placement is not useful to calibrate the field of view. And then here, the last example is an example in which the pole was placed outside, or actually in the limit, but let's say outside of the field of view. So this placement, again, this pole is not useful to calibrate the field of view. Okay. Actually, the more common are these three ones. Okay. So, and as I mentioned before, any of that will not be useful to calibrate the field of view. Okay. And yeah, Tancredi actually also explained or introduced that dual lens camera is not recommended for the European Observatory protocol. This is essentially because nocturnal and diurnal picture are different in terms of resolution. So we are working on that, and there are, let's say, several options. In case that any of you have a dual lens camera, in general, the better or the general recommendation is to don't use this camera. But let's say that some of you already bought this camera. So in this case, what we recommend is, for instance, using so calibrate the camera, the deployments during the day, and then use only diurnal picture to estimate density. Okay. Another option could be to calibrate the deployment during the day and during the night. So then we have a specific calibration for the daytime picture and a nocturnal calibration for nocturnal time picture and nocturnal species. So then we can use each calibration for each species. But this, as you can see, it complicates a little bit the process. So in general, don't use these dual lens cameras. And in case that you are using these cameras, maybe the simple solution could be to use only diurnal picture to estimate population density using the diurnal deployment calibration. Okay. So this part is just a brief introduction. So because in the next training course, which if I'm right, it will take place in September, we will better explain all this part. But essentially, in case of some of you want to start to process the data and so on, so when we come back from the field with the picture, with the memory cards, we should upload the picture to Agouti, and then when we start to visualize the sequence of a given deployment, the first decision that we have to do when checking the picture is to identify if this sequence corresponds to an animal or to a blank to a false activation, or in this case we are calibrating the deployment. So essentially all of these pictures with the pole correspond to a deployment calibration. So we have to click here in the deployment calibration button, and when we click here, we automatically obtain these two windows. So as you can see, we have to indicate the bottom stick height and the top of the stick height. So in this case, for instance, we can see 1, 2, 3, 4 marks because it's the upper mark. So we know that this is 4 marks, so it represents 0.8 meters, 80 centimeters. So we click here on the upper mark of 80 centimeters here, and then we do the same with the bottom mark, in this case 20 centimeters, because we can see only one mark. Okay. And we have to repeat this process with all the picture where the pole is resting in different location, and we always indicate the height of the bottom stick. If we are working in a grassland point, for instance, maybe the bottom stick is not identifiable, but we can use as the bottom of the stick the second mark, so we can indicate the step of 20 centimeters, 40 centimeters, for instance. And sometimes we can see, instead of the 80 centimeters as here, we can see the 1 meter mark, or we can see the 60 centimeters mark. The important point is that we need to mark the bottom and the upper marks that we are able to identify in each picture, okay? And we have to do this process when the pole is perpendicular and resting on the ground, as the example before, and where at least 2 marks are visible, okay? And as I mentioned before, we need to calibrate the lower and the upper one. Yeah, this is also important for you because you know that, as Tancredi mentioned before, cameras will be set in burst mode, so we have multiple or consecutive pictures, usually less than 1 second apart. So we will probably have more than 1 and more than 4 pictures of the pole placed on exactly the same location, exactly the same. So in this case, we just need to calibrate one of them. So if the pole is resting exactly in the same location, just calibrate one of them, then skip the picture and calibrate again when the pole is in a different location, okay? So when we do this process, we calibrate the picture, we will click here, automatically will appear this option, which is preview plot, preview calibration plot, and you will have something like that, something similar like that. This deployment obviously will be this plot will be deployment specific. I mean, you will never get the same plot like me here because these plots correspond to a given or to a particular deployment, okay? But essentially, you will have something similar. So the left plot indicates, it's a representation of the pole. This vertical line indicates the location of the plot, and this, you can see here, black dots indicates the height that we calibrated, okay? So as you can see here, we have from the left side to the right side plot, then some of them in the central, and we also have some poles calibrated far away from the camera, okay? Some of them very close to the camera, we essentially have these two and these two and this one, and other ones, also the one that are here in the background, correspond to the pole placed far away or at longest distance from the camera, okay? And then we have this second plot on the right side, which is a little bit maybe more difficult to interpret it, but essentially in the vertical axis, what we have is the distance from the camera, okay? So in this case, in this deployment, the maximum distance that we are able to see is around 12 meters. And then each of these points correspond to the location of the pole, okay? So in this case, we have more or less around 20 different locations of the plot. So each of these points correspond to a location of the plot, and then these 3 lines indicate us how too sloppy is the field of view. If the lines are very close, or is a perfect overlapping between the 3 lines, indicate that the slope of the ground is 0 or almost 0. As the lines are separated, indicates that the slope of the field of view is higher, okay? But in general, the most important thing when we are visualizing this plot is that all of these points are between the lines or exactly on the lines, okay? As we can see here, all of these points, only this one, but it's not a big problem, is slightly far away or outside of the lines, but the rest of them, all of them are inside of the lines. So here we have a good, a perfect good calibration, because we have really a very high number of pole placement, more than 20 here, probably more than 25. And as I mentioned before, the 3 lines are the three lines are very, very close, or are very close. And this indicates that the camera was perfectly aligned with the ground plane. As you can see here, this picture corresponds to this calibration. You can see here that the slope is 0 or almost 0. This is why the lines are very close one to the other, okay? In this case, this is still a good calibration. You can see that, as I mentioned before, all the points are inside of the lines. So this is good. And as you can see here, this is, I think, a good example. You can see here that the distance, there are some distance between the line. The lines are separated. So this indicates, as you can see here also quite well, I think, that there is a slopey, the field of view, we have a slope in front of the field of view, and this is why the lines are separated, but still this calibration is good, and we can use, and this is an unusable deployment to estimate population density, okay? And then we have 3 examples of bad calibration. So in this case, there are 2 problems. The first one is that we only have 3 points, so it indicates that we only place the field of the calibration pole, in 3 different locations in the field of view, and additionally, the lines are quite separated, as you can see here. So it indicates a very, very high slope and definitely a not usable deployment. Okay, so we need to, in this case, we need to come back to the field and put the pole in higher number of location. In this case, we have essentially the same. That's it. We only have three pole location, 1, 2, and 3. In this case, the lines, even separated, are more closer than in the previous example. But still, we need more points. We need to come back to the field and place the pole in a higher number of location to have a good model, a good calibration model. Okay. And then this is a particular case, and maybe more common for most of you, which is a situation in which we have these lines with a relative good separation. Let's say most of the points are between or inside the lines. Some of them are slightly outside the lines, but this is not a problem. But more important, we have these 2 outliers here, this one and this one. And in this case, it could be just a situation in which, for instance, instead of indicating when calibrating the picture, instead of calibrating 20 and 80 centimeters, we unintentionally indicates that instead of 20 centimeters, it was 40, let's say, or 60. Then obviously this particular calibration of the pole in one place is biased, so it represents a bias in one place and a bias in the other, in the other pole location. But it could be also that, for instance, we calibrate the pole without resting on the ground. Okay, so we can maybe calibrate 20 and 1 meter max properly, but in this case, if the pole wasn't resting on the ground, then the calibration, this particular calibration will be biased. Okay, so in this case, if we have a situation like this one with the points here or maybe here, essentially out and far away of the model of these lines, we can always come back to Agouti and check the calibration, check all the pictures that we calibrated, and probably we will found this. We will see that as we predict, we calibrate the ball without resting on the ground, or instead of indicating 20 centimeters, we indicate, for instance, 60 centimeters, something like that. So we can correct on Agouti these 2 ground location, and then plot or visualize this model again, and then these points will be placed probably around here, and this one around here, some place inside of the 3 lines. Okay. So summarizing, to apply photogrammetry, we need first the calibration pole, and you have this video showing how to do the calibration pole. Then we need to calibrate the cameras, and as I mentioned before, the European Observatory team provides you this work. So this is implemented in Agouti. You have it's nothing to do from your part. And at the end, which obviously you have to do this part of the work, you have to calibrate the deployment. You have to calibrate all these 36 or 45 different deployments that Tancredi mentioned before. So you have to do that on the field, and then combining these three points, we obtain photogrammetry, which allow us to estimate the animal position in front of the camera and to estimate population density, and as we will see in the next training course after the summer. Okay. So now I think that it's time for some questions in case of any.
If I can, I have just a question about the. So good morning, everybody.
Yeah. Morning.
About the slope. Before we say that the best position is to collocate the camera watching the north. If I have a double slope situation of the north, I can. It's better to change the area I'm looking for insight near the, around, or just moving the camera like on the south or on the east.
Yeah, in this case, I will say that it's more important to place the camera in a point with only one slope in front of the camera, even the orientation is different to the north. Okay, especially if you are in a forest, then the orientation is not relevant. The orientation is more relevant when you are in an open area, because, for instance, if your camera is facing to the east, then in the sunrise you will get many.
Exactly.
Yeah, this is the problem. So if you are in a forest, for instance, then obviously the orientation is less relevant, let's say. But even if you are in an open area, you have to. I mean, if the camera is placed in a sampling point or in a location with more than one slope, then this placement will not be useful to estimate density.
Yeah, for sure.
Okay.
Okay, thank you.
Thank you to you. Any more questions?
Yes, Diego has a question.
I think Diego also.
Diego, I don't know if maybe you're muted.
There's one question on the chat. So yeah, the question in the chat is regarding the slope calibration. If I understand correctly, when the camera is facing uphill or downhill, both the camera and the calibration pole must be perpendicular to the ground. Yeah, this is right. When the camera is facing the slope sideways, so that sees a diagonal line. Both the camera and the calibration pole must remain vertical. Let me check. Yeah, this is what you say at the beginning. The camera is recommended to be perpendicular to the ground, or which is the same, the sensor parallel to the slope. So the camera perpendicular, but the sensor parallel to the slope of the ground. And yeah, and the sensor the sensor should be perpendicular to the camera. The pole should be perpendicular to the camera sensor. So, which is the same, if the camera is perpendicular to the ground, then the pole should be placed in the same way, perpendicular to the ground and parallel to the camera sensor. Yeah. Yeah, this is, thank you, Marcus. This is what Marcus said now on the chat.
Great. Any other questions? If you have any doubts, this is a good moment to try and sort it, or if anything was unclear, even though I think the presentation was very clear, but if anything was, if you still have any doubt, please, Astrid.
Yes, thanks. Maybe it's rather to Agouti already applied. We realized, maybe we just don't know it, that if we click on deployment calibration, and it was a mistake, like this sequence is actually not a deployment calibration, but it's an animal moving through, we can't undo this deployment calibration anymore. So this sequence is basically then blocked forever as a deployment calibration.
Okay, so, well, if I can, Pablo, I think this this is probably some sort of a bug. So in this case, you should contact the Agouti team.
Okay.
I'll share, if you don't have it, I can share their email.
No, I have. So they will undo this deployment calibration move.
Yes,
okay.
they'll sort it. It's not a big deal. They should be able to sort it quite easily.
Is it possible that it would be implemented as with the animals, that oh no, it's like a wrong animal and you can delete your annotation? Would it be possible to just delete your calibration? But maybe I can just forward to Agouti. I think that's quite a specific question.
Yes, but it should be. I think it should be. But yes, they for sure be able to give you more details about that. But it usually should be possible to do that.
Okay, thanks.
You're welcome. Any other questions? Okay, so if not, I would like to thank Pablo for okay, yeah. So also Marcus encountered the same issue, and he also asked the Agouti team to fix this this issue. So they're probably working on it already. So thank you very much, Pablo. It was very clear. And so if you agree, I would move to the next presentation, which is going to be very short, so that we are sure that then there's some spare time for some more question time if needed, and for the pager presentation from Joaquin. So
thanks, Tancredi.
You're welcome.
I'm going to share the screen.
If that's okay for you, I'll finish first the last presentation so that we conclude the training course, and then you present the pager. Would that be okay for you? Okay. Great. It is not gonna take long. It's just the overview about Agouti and the analysis. So it should be about 15 minutes or so. Right, so you should now see my screen in presentation mode. So as I said, this is just going to be an introduction, an overview about the two topics that are then going to be targeted in the next training course in September. Some of these aspects have already been mentioned by me and Pablo in the previous presentations, but this is, yeah, so that you already have an idea of what are the following steps, and that you have an introduction in case you want to already have a look into them. You know what we're talking about and what tools we are going to use. So basically, how to fit photogrammetry in wildlife density estimation. Basically, we are estimating ecological parameters from pictures that we are obtaining in the field. So as Pablo mentioned, this was previously made manually, which was extremely time demanding and effort demanding. But with AI and specific tools for implementation of photogrammetry and data extraction, this can be done fairly easily and much more quickly. So what we use, as you know, is Agouti, which is an online open source platform for the management of camera trapping projects. There are other similar platforms like Wildlife Insights, DeepPhone, and others. However, Agouti has some specifically developed tools for the use of photogrammetry. So as any normal platform, you all have to register to it. Once you've done so, you're gonna have your dashboard, and there you're gonna see all the projects that you are allowed in. So basically, this is the workflow in Agouti. Once you've completed the field work, you're gonna import all your pictures, which are gonna be divided into deployments. Then you're gonna annotate them with the help of AI, if you like. And once that's done, you will then be able to digitize the animal sequences. These two steps, annotation and digitizing, are the most that are more time and effort demanding. But as I said, yeah, with the AI tools, this effort can be reduced. And once animal movements have been digitized, you will, for the target species, of course, you'll be able to create an export file, which is then a specific package of files that is going to be used in the analysis process. This is the dashboard. So this is a dashboard of Davide, a member of the EOW. And these are the projects that he was part of. So at first you're gonna see nothing in your dashboard, but then your project is going to be created, or you're going to be invited in some projects, and you will see the review of the project, allowing you to get into them, to enter the project. This is the menu of Agouti. So there's all the different pages. There's a general description, all the locations, the deployments. So from here you can manage all the files, and you can change the settings and manage the users. So invite new people or change their position within the project, allowing them to do something or not to do certain things. So someone might be just allowed to annotate the images. So that's very practical, and then it can be changed depending on what are your needs. These are the page where deployments are shown. So in Agouti terminology, a deployment is not necessarily made of all the pictures coming from a camera location. So most of the time they are going to be the same, because all the pictures that are coming from a certain camera location are going to be uploaded all together in a single deployment. However, if, for example, you have, and this might happen, you have a camera location where a very large number of pictures were taken, let's say like 50,000, this could happen. You might, in that case, want to split the pictures into two groups, and you're gonna then upload them as two different deployments, but coming from the same camera location. So you might have 2 deployments during the same year with the same location name. Very useful things are the tags that you can create as you like, and they can be very useful to keep your deployments tidy and browse through them. So you could create tags for different sessions for different years, and so making very easy the management of the deployment. Then there's the observation section, where you are able, as you see in the top right corner, to filter by time frame. If, for example, because if you are going to repeat the same monitoring in the same study site for more years, you're gonna keep using the same project. So you're gonna have observations from different years. So you will be able to select, let's say, 2023, the period of 2023 monitoring, if you only want to see those observations. Similarly, you can browse, you can filter by all these things that you see. So scientific name, age, sex, deployment ID, so that you can easily browse through the observations. This is what the Agouti interface looks like when you are navigating through a sequence. Very useful tool is the photo editing tool, where you can regulate brightness and contrast. This is going to be very, very useful at night for nighttime pictures to have an optimal view of what's going on in the picture. And then there's a photo preview at the bottom, where you can, which makes the browse through the pictures much easier. This, as Pablo has shown earlier, is what it looks like for the deployment calibration digitizing. He has already spent some words about that, so I'll move on. And as I mentioned, there's the possibility to use AI for the classification. Next to the scientific name of a substropha, you'll see that small robot icon. That means that this observation has been created by the AI, and yes, which is going to be something very useful, which is getting better and better, and it's going to be very useful. Here, on the other hand, is what it looks like when you're performing a manual annotation. So here you see there's all the different boxes where you can manually edit, change. So the species, you can specify the amount of, you have to specify the amount of animals, and you can specify the age class and the sex class of the animal, as well as the behavior class. And then you will see in the second training course, well, this is going to be explained in detail, how to track the animal movements within the sequences. This is going to be done after the annotation. So first, all the sequences are going to be annotated. Then once that's concluded, you will be filtering by species in the observation and digitizing a certain number of sequences. As you can see here, the sequence has already been digitized, and the animal movement, this deer movement, have been tracked. And browsing through the pictures, the point of contact between the animal foot and the ground has been marked with this points that you see in the picture. As for the species that you will be able to choose in the manual annotation, you will basically be asked, when defining the setting of the project, to add a species list. Otherwise, the species box is going to be empty when clicking on it. And so in most of the cases, the Western Europe species list is going to be the correct one. However, if a species was to miss, or for example, there's in the study site where you were performing the monitoring, there's, let's say, an alien species that was not included in the Western Europe species list, you will be able to manually add it, clicking on the Add Species button and browsing through the species. Here, basically, you see a test of how the AI classification is doing. And as you can see from the bottom values, both the deep found model and the Western Europe 4 model were doing pretty good. But now new models are also available, not just for these two deep found and Agouti models, but there's others as well. So you can choose between different versions of the AI. There's also a version that only digitizes for you blank pictures and pictures with human. So there's a wide range of options, and they're very useful and doing really well. What is important for you anyway, if you're using the AI, is that you still have a check of whether the AI had everything correct, because it might get a few things wrong, and especially what is still a bit tricky for the AI is the number of individuals. So most of the time it is going to get the species right, but not always the number of individuals is going to be right. And as you understand, it is crucial for us that the individuals in the sequences are correctly counted for the estimation of densities. So once your work on Agouti is concluded, you will go to the export data section and click on create export. So you will see that Agouti will start working and loading. And at that point, it is going to take some time. So you will be able to close the internet, do something else, check a few hours later, because it is going to take some time. And once that's done, you will be able to download your export file. Export file, which is made of a data package and 3 CSV files with all the information about your project. So there's going to be a deployment file, a media file, and an observation file. Clearly, we already have online some tutorials about this. So you can find the second training course from last year, which is already available online if you want to have a look at it. Clearly, the September one, the upcoming one, is going to be more updated. So we clearly recommend to attend that. But if you are interested in it and you want to have a look at it, you can find on YouTube and on our website the recording of last training courses. Several papers have been already produced on these tools, and yeah, research have been conducted using these tools. So what happens next? Basically, once we have our export file, what we want to do, what we're going to need is our studio. And so here, just a recap of the formula that was explained before. We have all the encounter number, operativity of each camera as a T, day range, and detection zone. All these elements are going to be found in our export file, and we're gonna be able, following the procedure that Marcus Rocliffe has specifically developed, and that is found on his GitHub repository, together with example files, explanations, very clear explanations, and all the examples of each step. And so this procedure is very straightforward and easy to follow, so that anyone, even if you don't have a specific experience in the use of R, everyone is going to be able to follow this procedure and being able to obtain the density estimates on their own. So there's the procedure is basically divided in chunk of codes, each one for each step. Some of them are fundamental, like these, installing the right packages and loading the library, and as well as the data. Then some others are optional, so you will be able, if needed, to subset the deployment, to correct some timestamps, to slice some data for certain periods, to cut off some deployments that were not correct, and so on. And then once that is done, you will be able to choose which deployments to include in the data analysis, or at least to which deployments should be considered when deciding, when evaluating the quality of the plots, of the deployment calibration plots. So if some are not satisfying our requirements, we can just exclude them and only consider that specific deployment for the contact rate, and not for the estimation of day range and camera trap detection parameters. Then the RAM density estimation code is going to return us these results. Basically, these are examples taken from one of our reports, where you see these 4 study sites and the results they obtain with this procedure. So what you're gonna get is a trapping rate, day range, effective radius and angle. And please note that radius and angle in this case are going to be species specific. So these are the radius and angle which are obtained for the target species, which was which the analysis was run for, because let's say pine marten is certainly going to have a different radius and angle with respect to red deer. Therefore, radius and angle are going to result as a mix from the target species, the camera model, and the environment, because they're going to be an average of all the radius and angle from all the deployments, all the camera locations, which in some cases might have larger radius and angle, and some cases might have reduced ones. Then we have the actual density estimate together with the standard error and the coefficient of variation, and in the end, the number of sequences obtained for that species. As mentioned before, this year a new procedure was developed. I mean, what was just said is just the same, but there's a final code that is where you see an example here in this slide, which is used to produce a CSV file, which I'm gonna show you in a moment, that summarizes not just the results, the estimates that I've just shown you, but also some additional information about the monitoring, and that are standardized and reduce the risk of mistakes in transcriptions, and so which was a very useful step in our data collection. So here you see an example. The command is write RAM CSV, and in the brackets there's an example here of the names of how the results for those species were called. So here you see 3 objects which are separated, each one separated by a comma, but they could be 1 if you only had 1 species analyzed for that specific study site, or it could be 10 if you so any number. The important thing is that each object is created as an output call from the RAM estimate command, so that R can take the information and the results for that call and summarize them into the CSV file. That is going to look like this. So you're going to have some of the names are not fully shown, but you have project name, data package, sampling ID, the minimum and maximum latitude and longitude, to have a better idea whether there's some mistake in the coordinates, start and end, the effort in terms of days, the species analyzed, and then the number of observations obtained for that species, and then the actual estimates, those that I've been mentioning before, and together with the units at the end and the n, so the elements used to obtain that estimate, the single estimate. Clearly, it is fundamental for us to the collection of this data, because the creation of the new EOW database is going to allow us to make further analysis and publications like the one that Joaquin is going to introduce shortly. So this was it for this presentation. I don't know whether there's any question about this. Clearly, as I said, there's going to be a chance to see all this in detail, but if you have any curiosity or if anything was not clear, there's time for answering questions. If not, I will just introduce what Joaquin is going to tell you about. And
there is one question, Tancredi.
Yes, please. Please, Diego. Okay. So Diego asks if the script that is being developed to create reports is going to be available anytime soon. It is going to be finalized. I can't tell you a date, but I'm pretty sure that they are sorting the last things, because a few months ago was already at a very good point. I'm afraid that Patrick, who's the person dealing with the development of the script, is not here now, so there's probably no chance to have further details about that, but I'll make sure to also give you a general update to everyone about this topic as well, because for those who don't know, Patrick, who's one of the members of the observatory, was developing a script to basically produce an automatized report of the activities carried out within a each project in Agouti. So this tool clearly will be very useful to anyone participating in the activities of the observatory, as this automatized version would create a report summarizing all the information about the project, about estimates obtained, and so on. So hopefully I'll be able to give you an update very soon. So it is asked if the slides from today's training will be available to review them. Sure, of course, we will share them. We will share them together with the minutes. And so, yes, certainly they will be available together with the recording, actually. So if any doubt, you will be able to watch it back. And of course, I'm also always available for assistance. So if any further doubt arises, you can contact me and we'll sort it together. Any other question?
Hello, I have a question. How do you count double counting of individuals? Is it included in the formulas? I don't know if there is something for that.
Sorry, could you please repeat? I'm not sure I got it right.
How do you count the double counting of individuals that we can have, for example, in front of two cameras that are close? If it's the same animals for the double counting, do you have something included in the formulas?
Yes, I mean, the random encounter model does not, the spatial autocorrelation is not an issue here, because we are dealing with non-recognizable individuals. So for what we know, it could always be just the same animal moving extremely fast. But the fact is that we have in the formula, we have the distance traveled by the animals. So we have the average distance, which is traveled by the animals. So including that in the formula is going to allow us to take into consideration this possibility. So the higher the distance traveled by a certain species is going to be, the lower the overall density is going to be, because as I was saying, if a certain species moves a lot, then few animals might create more contacts. Does it make sense?
Yeah, thank you a lot.
You're welcome. Any other question? Okay, so if not, I'll just quickly introduce the paper proposal file and then leave the floor to you, Joaquin. So basically, what you see here is the paper proposal file that has been created. Basically, each collaborator that has been successfully providing results in the activity of the EOW is going to be allowed in, and you will be able to propose paper, and here there's instructions on how to do that. Then you're going to have the list of proposals, and there's a format that you will be able to duplicate and then to fill in. So here's an example on how to do that. You will have to describe it, state the name of the title, the name of who's proposing it, and if there's a deadline, you can specify. then the data that you want to request and the metadata that you might need. Then the participants who are allowed in the proposal file can register, stating that they want to participate with their data to this paper. Whoever proposed the paper is then going to lead the activities. And so I'll leave now. So this is how it works generally speaking, and I'll leave now the floor to Joaquin, who is going to introduce a pager from IREC. Please, Joaquin, whenever you want.
Thank you. Okay, sharing my screen. Okay. So, good morning, everybody. Nice to see all collaborators, but also new people interested in joining the observatory. Tancredi introduced what a pager is and where you can access to the list of pagers that people is proposing. It's a specific proposal in order to promote the collaboration, the participation of different participants of the observatory. Maybe most of you are new to the observatory, so you haven't yet generated information. But anyway, in the near future, you will be interested in participating at even proposing pagers, because at the end, the main of the philosophy of the observatory is to be collaborative and to take mutual benefit of what we are doing in a harmonized way. So this specific pager will be part of a master thesis by Matteo Arseni. Matteo should be there, listening the meeting. And there are different colleagues of the observatory that are participating in the coordination of the pager. But the idea is this to be open to anybody interested in participating. So you can see the details of the pager in the field that Tancredi commented before. So, and which I'm going to introduce next. So the background behind this proposal is the growing interest, which is not recent, but there is growing interest in better assessing the distribution of wildlife species. Particularly, we are focusing on medium-sized to big-sized mammals, because this is important to administration, to policymakers, to assess biodiversity conservation and management, and to answer many different questions. And particularly, there is a special emphasis on monitoring alien invasive species. So we believe there is an added value for taking information generated by networks of camera trapping, particularly networks that are well structured, that are following protocols, you know well the methodology and the strategy behind the data. So the general hypothesis of this study is that European networks of camera traps are capable to contribute to monitor change and expansion and distribution of species, with particular emphasis on animal invaders, but not only. Also, it's interesting for species we are shifting, are modifying, and increasing in some cases their distribution rights, not necessarily invaders. So there is a number of specific objectives of tasks to address this pager. So first, we need to collect information on the rate of the species detected by camera traps over this network of camera trapping. When I refer to networks, I refer mainly to the European Observatory of Wildlife, but some of us are also participating in other networks or projects or initiatives where people are also collecting data using camera traps. So we can open this pager to these to other networks. Okay, so we have information of the species that are detected in different study sites through camera trapping. Then we need to get information to compare to evidence the added value of camera trapping against what is known on the distribution of the species. So for this purpose, we are going to characterize the distribution of species at different levels. First, level 1, if this species is present in the area where camera traps has been developed, this will be assessed through questionnaires. I met the participants of these networks because they know or they manage information, in many cases gray information which is not published, on which species are present in the specific study areas, in the locations where the camera traps are placed. Then also, if this species is present in the region, let's say nearby of the study area, so this species is expected to be present, even when we don't have direct evidence that this species is present. And finally, at the large scale, there is kind of, let's say, official information or maps on distribution of species, which are normally managed for international, in international context. We are referring to maps, broad maps, not particularly very detailed, but broad maps done by organization by UCN that can be completed by observations included in GBIF. Also, the European Mammal Atlas is a source of information. So we need also to evaluate if camera trapping also is providing information on the distribution, of the updated distribution of species at this large scales. This is the 3 levels of information that we are going to compare camera trapping data. Okay, so we have the data from the site based on camera traps. We have the reference data for comparisons. We are providing an added value to monitoring. Then we need to cross this information to address the objective of the task number 4, to determine if this species that we detected by camera trapping has been previously unreported. Okay, and finally, we are going to analyze the results in terms of which factor can determine this capacity to detect these species that are changing their distribution range, with a special emphasis to alien species. How we are doing to address that? Okay. Here you had the same list I commented before. So we need to collect the data about the species that are detected or that are not detected but probably are present in the different study areas. For instance, the study areas of the observatory. This data already is shared by you or by former or all participants of the observatory, because we had a collaborative database where we indicate the species that we detect. So the action we need to do is to complete this table. In some cases, for many species, this table presents blank cells. So we need to indicate, okay, it's blank, but it's because this species has not been detected or is not present in my study area. So we have to check this table in detail. Tancredi, we will contact you to coordinate this action. Next, we need this data, as I commented before, on the range of species that are present in the study areas And we also need to collect information of the species that are present in the region or that are present according to this official source at that scale. So the idea is to use a questionnaire to be filled by partners. In the case of the observatory, you already are using a shared database. So probably the best approach is to use this database, which is already built, to be completed. So the details about how we are going to do that will be provided to you soon, okay? Because we need to discuss with Tancredi and Massimo what is the best option. Maybe we can create a new shared document or questionnaire where you can indicate this information. And about the large-scale distribution of species, Matteo Arseni, in collaboration with other partners, is collecting information and to generating cartography on the distribution of all these species. So, in order to provide more details and deadlines and to frame the next actions, first we ask is partners to indicate they will to participate in this period. For that, you can insert your details in the shared document that Tancredi commented before. Please do that, let's say, within the next 2 weeks, so we have a clear idea of which study areas will be included in that. As you can see, we only are requesting basically data on presence of species. So we believe there will be not important confidentiality issues about that. So we encourage all of you to participate in this period, which we believe will be really interesting. Particularly because we are demonstrating the value of such a network of camera trapping to provide monitoring data at international level. So this is, I think, this page is quite interesting to show that. Okay, about filling your data, about species that are present, not present, or not detected in your respective study areas. As I commented before, we are going to provide you details soon where you can fill this data. But let's say having this by 20 May, the last part of May will be fine. It's quite a straightforward questionnaire that you have to fill. So this is, for example, a shot of the table that we are sharing about the presence of species in the different states of the observatory. So you can see that in most cases, the people already is providing data on the presence of different species. But in some cases, we have some cells which are blank, or we don't know the species is not detected or is not present in the area. So we need to refine this database, not only for this project, but in general, to make sure we manage, we know the information we are managing. And we also manage a table about the main characteristics of different study areas, the size, the management, etc., etc. So this probably can be the database that we can use to collect this information on the area. All right. Anyway, as I commented, soon we are going to contact you about where you can fill this data. So having that by the end of the May of the month, next month will be okay. About the species we are referring to, basically they are the species that are listed in this table that I commented before, that is shared among all partners of the observatory. But we are referring to a species that normally can be detected through camera trapping when cameras are deployed in the field, following the same approach that we are doing at the observatory. Okay, so let's say small, medium to big size mammals, maybe the smaller are animals like small carnivore hedgehogs, some lagomorphs. Okay, from this size to big animals would be included. All this information would be provided in the table that you need to fill. And the same for information on the study site, okay? So the aim is this information to be analyzed by the end of September. First, we'll take the save of a master thesis, but will be converted in a paper to be published in a scientific journal where all participants of the observatory will be co-authors. Obviously, after the first analysis of data, we are going to share with you the databases, and we will be open to receive all your input, comments, suggestions on the analysis and interpretation of data, and finally on the final version of the manuscript. All time, the approach is collaborative. So that is all for now. As I say, we will come to you all with details on how you can fill and share this information. And I hope this presentation also was illustrative for you to see how Pagers could be a very powerful tool for us to collaborate, to produce science, mutual benefit for every partner of the observatory. So thank you. I don't know if you have any question, but anyway, we are going to share this presentation. You have our contacts there, and we will be happy to answer any question in the future. Thanks, Macready.
Thank you, Joaquin. Yes, I think this is very good example of what can be the outcomes of the observatory. So for those who are new, this is an example of the potentialities of the observatory, and also a good reminder for all the members of the EOW to participate, to check the paper proposal file, and participate whenever possible or whenever they think the work can be worth, because yes, this certainly is something that benefits us all, and that allows us to take the most out of the efforts made in the field and in our offices to obtain the density estimates. So yes, thanks again, Joaquin. If anyone has questions about this last topic or anything else, we still have some time for question. If not, as I said, minutes of this meeting are going to be shared together with the presentations and together with the recording. So there's going to be some sort of summarizing of what has been said. So it seems like no question arises, so hopefully we were clear enough. And this said, I want to thank you all for participating. And yes, as I said, we will get back to you very soon with a participation form and details, recordings, and so on. Thank you very much, and have a nice. Bye, everyone.
Bye-bye. Thank you.
Bye. Thank you.
Bye.
Goodbye. Thank you.
Thank you very much.
Bye. Bye-bye.